There we go. Okay, so what I'd like to talk a little bit about today is a project that I currently started. It's a continuation of a project from about 15 years ago. That's looking at the sustainable utilization of seaweed resources in the Nordic regions, particularly in the Arctic. So, of course, we're all familiar with the bioeconomy. It's unfortunately become something of a buzzword. But when we think about this in the context of seaweeds, there are a lot of open questions that require a lot of really fundamental basic research into some of the sort of the underlying pinnings of sustainability. For instance, when we talk about seaweed, how sustainable is it to actually utilize seaweed? Is it okay just to go out and wild harvest? I mean, that's going to have some sort of environmental impact. How much seaweed can we harvest from a given location? How is this going to change as a function of seasonality? Is climate change continues to warm this part of the world? Uh, what about renewability of these resources? How quickly will these seaweed resources replenish? And what impact will this have on the other flora and fauna in that particular part of the ocean? There's also a great deal of missing knowledge about, the preservation of these seaweed resources. We have no idea what will happen when we actually start extracting significant quantities of these seaweed resources. What are the carrying capacities of these communities, and how is it going to affect, things like the fish species and some of the arthropods that might, sort of take refuge in things like kelp forests? So I'm something of a microbiologist by training with a little bit of background in chemistry. And when I look at macroalgae or seaweeds, I see a lot of fantastic opportunities. So ever since the 1970s, spent a lot of time in public funds trying to figure out how to make bioenergy from biomass. Mostly things like, cornstarch and lignocellulosic biomass, so woody plants and trees and grass and stuff like that. Now, seaweed, especially some of the green seaweeds, are particularly attractive when it comes to thinking about bioprocessing. So what I have pictured here is either Ulva lactuca or Ulva fenestrata. They're very difficult to tell apart visually, but it's a nice plant to work with because it lacks lignin. So from a bioprocessing standpoint, working with a species like Ulva is, potentially, feasible. It's doable with not too much uh, difficulty in terms of finding, selective degradation technologies and stuff like this. This, however, is not the case with some of the brown and red seaweeds. And this sort of brings us to one of the big problems with working with seaweeds. There's a lot of diversity in terms of the seaweed resources that are out there. They differ wildly in terms of their composition. While they like lignin, a lot of, for instance, the brown seaweeds contain molecules which are a lot more difficult to work with, things like fluorotannins that might require extensive pretreatment. They might also contain carbohydrates that are, particularly difficult to break down. So if you want to use, for instance, seaweed like ulva is a source of protein, which it typically has quite a lot of protein as a percentage of its dry weight. In some cases, up to 40% of its dry weight is protein. One of the barriers to using this as like a feed for instance, farm animals or fish, is that the amount of insoluble fibers due to some of the other carbohydrates present will actually give these animals diarrhea, which is not so great. But there are still some significant advantages. For instance, cultivating seaweed obviously doesn't take arable land. We can actually sort of couple the farming of seaweed to nutrient recovery efforts through things like, integrated multi-trophic aquaculture and stuff like this. And we can also, utilize the seaweeds as raw fertilizers. But there's a problem. That all has to do with, sort of, selectively farming specific things, specific species of seaweed. But what about situations like this, where we've got so-called beach cast seaweeds, in this case, slightly high tide, but in a lot of cases, these seaweed blooms will sort of basically lay on the beach and rot. Now, it's not necessarily a problem, but unfortunately, as the Arctic regions continue to warm, the growth range of a lot of these seaweed species will continue to spread further north. Where they're growing well, they will continue to grow even better. And for instance, with Ulva lactuca, which is a particularly problematic nuisance organism in a lot of communities, it's gotten a lot of bad press because it's been associated with these sort of anoxic events where basically you've had sort of a lot of ulva grow in a particular location, die, rot in place, produce a lot of hydrogen sulfide, which will, do things like choke off, fish species that live in the area. Also smells particularly nasty. So what can we do? And how are we going to sort of help these communities that are going to be potentially impacted by this sort of coming inundation of seaweed? Recently, some partners and I scattered across Scandinavia, ranging from Greenland, Svalbard, Norway, Sweden, Denmark, and we're trying to rope people in from the UK. Recently, got a project funded through Nordfosk. We're actually sort of trying to set up a consortium that will sort of look at low-tech approaches to finding seaweed solutions in the Arctic region. Now, it's just a small little pilot project, but it's particularly exciting. So, for instance, if we think about the challenges in the North Atlantic, there are many. But if you look at like the way populations are distributed, in a lot of cases, the infrastructure necessary to sort of harvest and process things like seaweed or anything really are very diffuse and spread out. About 15 years ago, I actually pitched this idea of sort of what did I call it? Decentralized bioprocessing, and it was sort of laughed at as being unsustainable because we should concentrate everything in large cities. But as sort of the decade is, or I guess the century has marched on, I think people are starting to sort of reevaluate this and realize that we need to get resources to deal with some of these problems at the local level. We can't just transport everything to a central location. We sort of need a sort of a local way of dealing with these problems. Now, another major challenge in the Arctic is the cost of energy. Here in Iceland, we're a little bit of a special case because we've got cheap, abundant, hot water, more or less guilt-free energy, more or less. But a lot of rural communities in the Arctic don't have these resources. So, for instance, there's been a lot of public funds dumped into producing, for instance, biogas from seaweed, but a lot of that work has largely gone nowhere because they've taken sort of a very traditional approach where basically you put up an anaerobic digester, throw a bunch of seaweed in there, maybe a little cow manure as your source of bacteria and other goodies to break it down. And the end result is very lackluster. You don't get a lot of energy out for the amount of energy you actually put into the system. That's a bit of a problem. And it's also a very tall ask for rural communities that are already, maybe looking for other sources of energy instead of, buying it at an exorbitant price. The other major issue with rural communities, particularly in the context of seaweed processing and a lot of other supply chain issues, is the transportation distances involved. So we really sort of need to start thinking about, how can we sort of utilize resources like seaweed to support the local economy that doesn't involve transporting things great distances. So that's one of the things that this consortium is looking at. Now, my research group, one of the things that we've been working on is actually sort of looking at how to process seaweeds, particularly some of the green seaweeds, because they're just kind of fun to work with. How can we sort of process them using sort of novel approaches? And by novel, I mean find old school approaches and repurpose them. So for instance, if we come back to this idea of anaerobic digestion, so typically, and I apologize, I did have animations on this slide. The traditional approach to anaerobic digestion is you take seaweed, you throw it in a digester, add some cow shit, let it, ferment. Sorry to be crude. It's awful stuff. Horse is better, which, I prefer horse dung over pig feces. Just no, it's a non-starter. Anyway, typical approach is to basically just take your seaweed or whatever biomass you like, throw it in a digester, heat it up to 35 degrees, and collect your biogas. Now, in the Arctic, that's a bit of a problem. We already see that problems with landfills experiencing problems with the very, very slow decay of biomass. There was a story a couple of years ago here in Airfield where somebody dug up an apple that looked pretty fresh from the landfill, and it was dated back to like 1930 or something like that. So there's not a lot of energy for breaking things down in the Arctic. So why don't we actually just lean into that? Why treat it like a problem? Why not actually go the extra mile and just accept it for what it is? Now, the consequence of that is if you do anaerobic digestion at a low temperature, instead of producing biogas, you're going to get what's called an incomplete digestion, which is basically just a way of saying that the biomass in the digester isn't going to produce methane, hydrogen, CO2. It's going to produce larger molecules like fatty acids, things that are sort of on their way to being broken down to hydrogen, methane, and CO2. Now, why would we want to do that? That seems like it's kind of counterintuitive. Well, the nice thing about these fatty acids, they're actually a very, very valuable product in their own right. So what I've got pictured here is butyric acid, which smells like feet. It tastes much better than it smells, I can assure you. But this butyric acid is a very, very valuable additive to, for instance, animal feed. So there's a lot of evidence that suggests that by feeding animals butyric acid, which is sort of something that happens when we eat anyway, the bacteria in our gut and animals' guts, will basically ferment sugars and other things to things like butyric acid. This can actually have sort of a very positive impact on the gut microbiota of animals. And they'll basically, sort of produce less methane and other greenhouse gases as a result. The other thing we could do with molecules like butyrate is we can esterify them. So we can actually turn butyrate into butyrate methyl esters, which we can actually use as sort of an alternative low boiling biodiesel. So we can actually sort of rope it back to a bioenergy approach. If we get really brave, there are actually bacteria out there that can actually convert our butyric acid into butanol, which is another potential biofuel, which might be applicable in the Arctic. Now, one of the problems with using anaerobic digestion, though, at low temperature is, I mentioned normally we produce, a lot of hydrogen, methane, CO2, stuff like that. But at low temperature, a lot of bacteria aren't sort of organized metabolically to actually do this type of chemistry. So why not find bacteria that are adapted to do this type of chemistry? And this is where sort of working the Arctic comes back in. Again, lean into what we've got. So for instance, here we've got a picture of some sheep grazing on seaweed in the Shetland Islands. Here in Iceland, we've also got sheep that graze on seaweed along the coasts. So why don't we sample the sheep in their rumen, which, where it's just sort of the forestomach, where there are bacteria that sort of break down seaweed and other stuff, take those bacteria and use that in our anaerobic digesters with the hope that A, it will work at a lower temperature, but also those microbes will be sort of better suited to actually break down and utilize the seaweed. So that's one approach that we're looking at. Now, the problem is this always comes back to economics. Unfortunately, biogas and a lot of these low value molecules really, they're very difficult to break even, particularly when you sort of look at the challenges and the cost of doing this in the Arctic. So one thing we can do is we could lean into some higher value products that we can actually utilize by breaking down the seaweed in its own right. So for instance, uva lactuca is an excellent source of a sugar called rhamnose. If you've never heard of it, I wouldn't blame you. I can assure you it tastes sweet like most other sugars. But there are a lot of bacteria out there that will actually take rhamnose and break it into this molecule here. It's called 1,2-propanediol. This used to be a specialty chemical, but these days we actually find it in everything from windshield washer fluid to as a building block to make pharmaceutical molecules. And what's interesting about 1,2-propanediol, and this is probably one of my favorite molecules, it actually exists as two forms in nature. There's a left-handed form. I can't believe I got the hand right this time. There's a 50% chance I'll get it wrong, and a right-handed form. Now, if you can separate those two molecules, this goes from being a bulk molecule that's worth, I don't know, maybe 10, 15 bucks a kilo to something that's worth on the order of $40,000 per kilo. So if you can find a way to do this selectively at low cost from seaweed using the sugars already present in seaweed, you've actually got quite a high value proposition there that you can use to offset the cost of producing these other low value molecules while dealing with the seaweed problem at local levels. So I won't talk too much more about this. I could go on forever, and I apologize. I actually designed this lecture to be sort of a quick and dirty, truncated lecture, as I assumed I would let everybody else speak for too long. So I'll happily take any questions at the end, and thank you for your attention.